the ideal gas equation. Now, this is one of the most important parts of this chapter. The ideal gas equation is basically a consolidation or an inference, we can say, of all the gas laws that we've studied. So let's first list down what gas laws have we studied as yet. When the temperature and number of moles is a constant, let's put a heading as constant here, and here we'll have the relation and here the name of the law. So when the temperature and number of moles are a constant, the relation is what? P is inversely proportional to V, and this was named as the Boyle's law. Then when the pressure and number of moles were constant, we had volume as directly proportional to temperature, and we had named it as the Charles law. And when the volume and number of moles were kept constant, we had the relation as pressure being directly proportional to temperature, and this could be called as the Gay-Lussac law. These were the major laws which we had studied. And if you remember, a constant temperature would mean, let's say we have kept the temperature constant at 27 degrees Celsius or something of that sort. A constant pressure would mean, let's say we have an open container which is not letting moles escape but is open to the atmosphere, and the pressure is PATM. And let's say for a constant volume we have a given box in which the gas is being kept. Okay, these are the physical significances of these conditions. So on combining these conditions, we can say that pressure is directly proportional to Nt divided by V. And this thing can be interpolated by giving it a proportionality constant, that is P is equal to nRT by V. Now here R is the proportionality constant which we use, and our ideal gas equation, which is very, very important, becomes PV is equal to nRT. It is one of the most important things in this chapter which you would be studying. Mark the ideal gas equation as important. Now let's talk about what this R is. R is called the universal gas constant. And remember that it is a constant and is universally true, and therefore it is not dependent upon any of these parameters. It is an independent quantity, and the value of this constant is 8.314 when the units are joule, Kelvin inverse, mole inverse. The value becomes 0.0821 when the units change to liter, ATM, mole inverse, Kelvin inverse, and these units change to 2 calories, Kelvin inverse, mole inverse. So basically when the units of our energy change from joules to liter ATM to calories, the value of R changes. However, the value of R does not depend upon any of the parameters: pressure, volume, number of moles, or temperature. And here an important relation which you might want to know is that 1 calorie is equal to 4.2 joules, and therefore there is such a change in the values. So this is the most important part of this chapter and is a very handy equation which simply combines all the three gaseous laws. Next, we have to derive the density expression from the ideal gas equation. Now let's remind ourselves what the ideal gas equation was. It was PV is equal to nRT, right? And according to our knowledge of density, how do we define it? It is defined by the mass, right, of a substance divided by the volume occupied by the substance. So we can say that we have a gas A, we have, let's say, m grams of the gas, and the molecular mass of the gas is capital M. So if I have m grams, I can say that the number of moles which we have is the given mass divided by the molecular mass. Now try to remember this relation. We had studied it as a part of the parameters of a gas when we had defined the mass of the gas in terms of its moles. So let's just substitute this quantity, the given mass, upon the molecular mass in our ideal gas equation. So the equation would become PV is equal to M divided by capital M into R into T. Now the density in this case would be defined as what? The mass of the gas is M and the volume it is occupying is V. So let's bring this term M divided by V together. This can be written as P is equal to M divided by V into 1 by capital M into R into T. And let's shift the other things on the other side. This would give Pm divided by RT is equal to the mass divided by the volume, and that is equal to the density, right? Let's call it rho or D, however you're comfortable. The takeaway expression from this density calculation is that rho is equal to Pm divided by RT. Now there is not much of a need to remember this expression because it is always very easily derivable.